In this lecture, we are going to study more examples of using rotating and translating reference frames. The first example is as follows. A system consists of two arms. The first arm has a length of L1 and is oriented an angle theta from what we're going to call the horizontal and is hinged at point O, where O is fixed to the ground. The second arm is hinged to the first arm and has a length of L2, and the angle formed between the first arm and the second arm is going to be labeled phi. The point which defines the hinge or the pivot between the two arms is going to be labeled Q, and then the end of the second arm is going to be labeled P. So the objective of this problem, given this information, is to determine the velocity acceleration of P, which is the tip of the second arm, as viewed by an observer fixed to the ground. Now, you can see in this problem that there are two rotations. So two rotations, which implies that we're going to need three reference frames, a total of three reference frames. Now, let's figure out what these frames are. So the base reference frame is the ground. It's the ground. And that's the frame in which I want all my rates of change in the end. And then I have two rotating frames. So the first rotation, or the first rotating frame, is arm 1, which I'm going to call A. And then the second rotating frame is going to be arm 2, and I'm going to call that frame B. So now let's go through and define coordinate systems that are fixed in each of these reference frames. So G is the ground, which, remember, is the base reference frame. And the coordinate system that I'm going to fix to the ground is going to have its origin at point O, because O is the hinge point of the first arm, and that's fixed to the ground. And then I'm going to put big EX is going to be along OQ when theta equals 0. That's effectively to the right in the diagram. EZ is going to be out of the page. And then EY is going to equal EZ crossed with EX. So that's the first coordinate system that's fixed in the ground. Next, I need to define a coordinate system that's fixed to the first arm. So this coordinate system is going to have its origin also at O, because O is also fixed to the first arm. And now I'm going to call these, I have to label these a little bit differently from what I may have labeled in previous problems. But I'm going to say E1 is going to be along OQ. And E3 is going to equal EZ. And then E2 is going to equal E3 crossed with E1. And then the last reference frame, which is the second arm, the coordinate system fixed in that frame, is going to have its origin at Q. And the reason I'm putting the origin at Q is because Q is fixed in the second arm. And I have to pick my coordinate system such that the origin is fixed in the frame in which I'm defining the coordinate system. So since this coordinate system is fixed in the second arm, the origin is going to be at Q. U1 is going to be along QP. U3 is going to equal E3, which also equals EZ. And then U2 is going to equal U3 crossed with U1. Now, let's draw a little diagram here and see what this looks like. So here is the direction E1. That's the direction along the first arm. Here's E2, and then E3 is out of the page. Then the angle phi comes into play. This is U1, this is U2, and then U3 is out of the page, and the angle here is phi, and the angle here is also phi. So from this, we can actually start to put together the position and then the velocity and the acceleration. So let's do the position first. So we know that the position of point P relative to point O is equal to the position of Q relative to O plus the position of P relative to Q. Now the position of Q relative to O is equal to L1 times E1. This is distance L1 in the direction E1 from, the distance from O to Q is L1, and then the direction is along OQ, so that's E1. Then the position of P relative to Q is equal to L2 times U1. Similarly, we're measuring from Q to P. The direction from Q to P is U1, and the distance between Q and P is L2. So that tells me that the position of P relative to O is equal to L1 E1 plus L2 U1. But remember that we're going to do the rate of change. We're going to compute the rate of change of each piece of the vector separately. We're not going to do it all at once. We're not going to combine all this, put it into a single basis, and then do the calculation. And the reason is because the observations of point Q, if you notice, we've expressed the position of Q relative to O, which defines how Q is ultimately going to move, in terms of a basis that's fixed in the first arm. And we've expressed the position of P relative to Q, which is going to define how P moves relative to Q, in a basis fixed in the second arm. So we're going to apply separate transports in each one of these pieces, and then we're going to combine the results to get the velocity. So we know that the velocity of point P, as viewed by an observer fixed to the ground, is equal to the rate of change in the ground of the position of P relative to O. But that is equal to the rate of change in the ground of the position of Q relative to O plus the position of P relative to Q, which is equal to the rate of change in the ground of the position of Q relative to O plus the rate of change in the ground of the position of P relative to Q. So this if I now do each piece separately. So let's do each piece separately. So this of course, if I write this out, this is the velocity of point Q as viewed by an observer fixed to the ground. And then this is the velocity of point P relative to Q as viewed by an observer fixed to the ground. So let's do these pieces now. The velocity of Q as viewed by an observer fixed to the ground, which is equal to the rate of change in the ground of the position of Q relative to O. Because the position of Q relative to O is expressed in a basis that's fixed in the first arm, this is going to equal d dt in A of the position of Q relative to O plus the angular velocity of A and G crossed with the position of Q relative to O. Now the angular velocity, well, let's do the first part. d dt in A of the position of Q relative to O is equal to 0 because L1 is constant and E1 is fixed in the arm, in the first arm. The angular velocity of A and G is equal to theta dot times E3. So therefore, the angular velocity of A and G crossed with the position of Q relative to O is equal to theta dot E3 crossed with L1 E1, which is equal to L1 theta dot E2. So that gives me that the velocity of point Q and G is equal to L1 theta dot E2. Now we have to do the next part. The velocity of P relative to Q in G is equal to d dt in G of the position of P relative to Q, which is equal to d dt. Now it's going to be in B because the position of P relative to Q is expressed in coordinates fixed in reference frame B. So this is d dt in B of the position of P relative to Q plus the angular velocity of B and G crossed with the position of P relative to Q. And again, just like we had with the first part of the vector, the rate of change of the position of P relative to Q in B is 0 because L2 is constant and U1 is fixed in reference frame B. The angular velocity of B and G, now let's go back to the diagram here. You notice that the arm 2, the second arm, rotates relative to the first arm and the angle defined by that rotation is phi, and then the first arm rotates relative to the ground. So the angular velocity of B and G is going to equal the angular velocity of A and G plus the angular velocity of B and A. We already have the angular velocity of A and G. We computed it. The angular velocity of B and A is equal to phi dot times U3, which gives me that the angular velocity of B and G is equal to theta dot E3 plus phi dot U3. But since E3 and U3 are in the same direction, that tells me that the angular velocity of B and G is equal to theta dot plus phi dot times U3, because I'm going to express everything in the coordinates fixed in reference frame B. So then, what do we get? Therefore, the velocity of P relative to Q in G is going to equal, well, before we write the velocity of P relative to Q in G, let's just write this cross product. The angular velocity of B and G crossed with the position of P relative to Q is then equal to theta dot plus phi dot times U3 crossed with L2 times U1, which is equal to L2 times theta dot plus phi dot times U2, which then implies that the velocity of point P relative to Q in G is equal to L2 times theta dot plus phi dot times U3. u2, which gives that the velocity of point P as viewed by an observer fixed to the ground, which is equal to the velocity of Q as viewed by an observer fixed to the ground, plus the velocity of P relative to Q as viewed by an observer fixed to the ground, is equal to L1 theta dot E2 plus L2 times theta dot plus phi dot times U2. And that gives us the velocity. Now, we need the acceleration. So the acceleration of point P as viewed by an observer fixed to the ground is equal to the rate of change in the ground of the velocity of point P as viewed by an observer fixed to the ground. But that's equal to the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground plus the velocity of P relative to Q as viewed by an observer fixed to the ground. And that, in turn, is equal to the rate of change in the ground of the velocity of point Q as viewed by an observer fixed to the ground plus the rate of change in the ground of the velocity of point P relative to Q as viewed by an observer fixed to the ground. Now that, in turn, becomes the acceleration of Q plus the acceleration of P relative to Q, both as viewed by an observer fixed to the ground. So the acceleration of Q as viewed by an observer fixed to the ground, which is equal to the rate of change in the ground of the velocity of Q as viewed by an observer fixed to the ground. Now let's go back. Remember that the velocity of Q is equal to L1 theta dot E2. So that's expressed in a basis that's fixed in reference frame A. So we're going to apply the transport theorem from A to G. So this gives me the velocity of the rate of change in frame A of the velocity of Q and G, plus the angular velocity of A and G, crossed with the velocity of Q and G. Now the rate of change in reference frame A of the velocity of Q and G is equal to L1 theta double dot times E2. Because L1 is constant, E2 is fixed in A, and theta is the only thing that's changing. The angular velocity of A and G crossed with the velocity of Q and G is equal to theta dot E3 crossed with L1 theta dot E2, which is equal to minus L1 theta dot squared E1. So therefore, the acceleration of point Q as viewed by an observer fixed to the ground is equal to the sum of these, which is L1 theta double dot E2 minus L1 theta dot squared E1. And then I just flip the order to put it in the order of the basis vectors. So next, the acceleration of P relative to Q as viewed by an observer fixed to the ground is equal to the rate of change in the ground of the velocity of P relative to Q as viewed by an observer fixed to the ground, which is equal to, now if we go to the velocity of P relative to Q, we had that expression from before. The velocity of P relative to Q as viewed by an observer fixed to the ground is expressed in coordinates fixed in reference frame B. So this is equal to d dt in B of the velocity of P relative to Q in G plus the angular velocity of B in G crossed with the velocity of P relative to Q in G. Now let's go through these calculations. d dt in B of the velocity of P relative to Q in G is equal to, well, if we go back to the expression for the velocity of P relative to Q in G, it's L2 theta dot plus phi dot times U2. L2 is constant and U2 is fixed in B. So I get L2 theta double dot plus phi double dot times U2. And then the angular velocity of B and G crossed with the velocity of p relative to q in g is equal to, and now the angular velocity of b and g is theta dot plus phi dot times u3 crossed with L2 times theta dot plus phi dot times u2, which is equal to minus L2 times theta dot plus phi dot squared times u1. So if we combine these terms, we get that the acceleration of p relative to q in g is equal to, well, we've got the first term, which is L2 theta double dot plus phi double dot u2, and then the second term, which is minus L2 theta dot plus phi dot squared times u1. And if I put that in the order of the basis vectors, we get that expression. So then we have to take the two expressions that we've gotten, one for the acceleration of q as viewed by an observer fixed to the ground, and the other one for the acceleration of p relative to q as viewed by an observer fixed to the ground, and we get the total acceleration, which is the sum of these two. So the acceleration of p as viewed by an observer fixed to the ground is equal to the acceleration of q as viewed by an observer fixed to the ground plus the acceleration of p relative to q as viewed by an observer fixed to the ground. So let's go back and grab the acceleration of q. The acceleration of q was right here. It's minus L1 theta dot squared E1 plus L1 theta double dot E2. So this gives me minus L1 theta dot squared E1 plus L1 theta double dot E2. And then I've got minus L2 theta dot plus phi dot squared U1 plus L2 times theta double dot plus phi double dot U2. Now you'll notice again that everything is not expressed in a single coordinate system or a single basis. It's expressed in two different bases because each piece of the vector is more conveniently differentiated to obtain rates of change using a different basis. There's no need at this point to combine everything into a single basis. At some point later on, when we're actually starting to do kinetics, which I'm not going to talk about now, but when we do kinetics, then things need to be put into one coordinate system, or they often need to be put into one coordinate system. Sometimes they don't. You can just leave them, but you can do manipulations without having to actually do full transformations. But without getting into all of those details, right now the main thing is that you want to do the calculations in the basis, or using a basis fixed in whichever frame is most convenient to do that piece of the calculation. In this particular case, it was most convenient to compute the velocity and acceleration of point Q as viewed by an observer fixed to the ground using coordinates that are fixed in the first arm. And it was more convenient to compute the velocity and acceleration of P relative to Q as viewed by an observer fixed to the ground in coordinates that were fixed in the second arm, and then combine the two results. So that's exactly what we have here. Notice that the first part of this expression is in terms of a basis fixed in arm 1, and the second part of the vector is in terms of a basis fixed in arm 2. And as you do problems that require both rotations and translations, you're going to commonly find that this is the way to do these problems in a tractable manner, and be able to keep, to bookkeep all of the information in a way that actually makes sense. Because what's really happening in this problem, if you think about it, is that point Q is moving in a circle relative to point O. And the first two terms in this final expression that we have identify circular motion relative to point O. It's circular motion of point Q relative to point O. The acceleration that is written there, which is the acceleration of Q, is circular motion of point Q. The second part of the vector, which are terms 3 and 4, which are expressed in the basis u1, u2, u3, which is fixed in the second arm, those terms actually identify circular motion of the second arm of point P relative to Q. So in other words, it's giving you the circular motion of how P is changing relative to point Q, and they're more conveniently, those computations are more conveniently done in a basis that's fixed in the second arm. So this is a two-dimensional problem that allowed us to be able to see how to combine these different pieces and then put them together to be able to obtain a single expression for the acceleration of the point that we were interested in. And in the next example, we're going to actually look at a problem that's not planar, and it's going to allow us to be able to see how to do some of these things in 3 dimensions. So the next example that we're going to study is as follows. This problem is set up like this. We have a shaft, and that shaft rotates about the vertical direction. Attached to the shaft is an arm, and that arm has length L. So the shaft rotates about the vertical direction with an angular velocity omega. And the arm has length L, and on the end of the arm is a disk, and that disk has radius r. So this is the full picture of this problem. The shaft is like I said, rotating about the vertical. The disk now rotates also. There's a point P that's on the end of the disk, and the angle theta made with the vertical direction is theta. So there's the disk, and then there's the shaft. And the shaft has length L. Now the objective of this problem is to determine the velocity and acceleration of point P as viewed by an observer fixed to the ground. And what we're going to denote here is that the shaft rotates relative to the ground. So here's the ground, and the shaft rotates relative to the ground, and the disk rotates relative to the shaft. Now, in order to be able to complete the picture on this problem, I'm going to label the center of the disk as Q, and I'm going to label the other end of this arm that's attached to the shaft by point O. So if you look here again, you're going to see that we have 2 rotations, in which case we need 3 reference frames. So now the goal of this is going to be able to figure out how to set up the problem so that we are able to align coordinate systems in a tractable way. So what are the 3 reference frames? So the base reference frame is the ground. Which I'm going to label G. The first rotating frame is the shaft / arm, because it's one rigid assembly. And then the second rotating reference frame is the disk. And I'm going to denote the shaft by S, and I'm going to denote the disk by D. So now let's start putting coordinate systems on these different reference frames. So G is equal to the ground, which is the base reference frame. The origin of this coordinate system is going to be at O. I'm going to put EX along omega, which is vertically upward in the diagram, and I'll explain why in just a minute. And then I'm going to put EZ along the direction OQ when t equals 0. Meaning whatever direction OQ is pointing when t equals 0, that's the direction EZ. And then EY is going to equal EZ crossed with EX. And I'll explain, like I said, in a minute why I picked the directions the way I did. The second frame is the shaft. The origin of the coordinate system fixed to the shaft is going to be at O. Now what I'm going to do is I'm going to say let little ex equal big EX. And I'm going to say little ez is going to be along OQ. And then little ey is going to be EZ crossed with EX. And finally, the third reference frame is going to be the disk. The origin of this coordinate system has to be fixed in the disk, so I'm going to put the origin at Q. I'm going to pick ER, and actually, yeah, we'll just call it ER. ER is going to be along QP, and then EZ is going to be the same as was used in S. So whatever that direction I defined along OQ, so you'll remember that that was along OQ. And then E sub theta is going to equal EZ crossed with ER. Now, if we actually look at this picture, we can actually see the following things, which is that EX is up. This is a little EX. EZ in this picture is going to be out of the page. And then EZ crossed with EX is going to give me EY, which points this way. ER is this direction along QP, and then E theta is going to point this way. So actually, if I want to do this with a little bit of less clutter, I'll put EZ over here, and then I'll put E theta to be this direction. This angle here is theta, which makes this angle also theta. So we know that ER, E theta, EZ is fixed in the disk. And we know that EX, EY, EZ is fixed in S. So now we're going to use that information to be able to start constructing the position. So we know that the position of point P relative to O, if you look back on the diagram, you'll actually see this. It's equal to the position of Q relative to O plus the position of P relative to Q. Now, let's suppose that I say that the radius of this disk, let's suppose I label the radius, I call it capital R. So then, the position of Q relative to O is going to equal L times EZ, given the way I defined EZ. and then the position of P relative to Q, this should be a Q, the position of P relative to Q is going to equal R times ER. And now what we can do is we can start taking rates of change to get the velocity. So the velocity of point P in G is equal to d dt in G of the position of P relative to O, which is equal to d dt in G of the position of Q relative to O plus the position of P relative to Q, which is equal to d dt in G of the position of Q relative to O plus d dt in G of the position of P relative to Q. Now you'll notice that the position of Q relative to O is expressed in coordinates fixed in the shaft, and the position of P relative to Q is expressed in coordinates fixed in the disk. So we can say that this is equal to the velocity of Q in G plus the velocity of P relative to Q in G. The velocity of Q in G, because it's equal to d dt in G of the position of Q relative to O, that's going to equal d dt in S of the position of Q relative to O plus the angular velocity of S in G crossed with the position of Q relative to O. d dt in S of the position of Q relative to O is equal to 0 because the distance L is constant and EG is fixed in the shaft. The angular velocity of the shaft as viewed by an observer fixed to the ground is equal to omega, which is equal to omega EX. So then that tells me that omega SG crossed with the position of Q relative to O is equal to omega EX plus LEZ, which is equal to, crossed with LEZ, which is equal to L omega, and EX crossed with EZ is equal to negative L omega EY. Right, so that takes care of that. And if we actually look back here, you'll actually see that the velocity of this point of Q it's moving in a direction such that you take EX crossed with EZ, right? Because EX is the first direction here, and it's fixed to the shaft. It's along omega, and then I put EZ along OQ. So EY actually points backward in the way I have this defined. So, and you can see that from the diagram here, that EY is actually pointed to the left, not pointed to the right. So what happens is now that's the velocity of point Q in G is equal to negative L omega EY. So now let's get the velocity of P relative to Q in G. That's equal to, as we already stated, it's d dt in G of the position of P relative to Q. But because that's expressed in a basis fixed in the disk, this is d dt in D of the position of P relative to Q, plus the angular velocity of the disk relative to the ground crossed with the position of P relative to Q. And again, the rate of change in the disk of the position of P relative to Q is equal to 0, because if we look back on the expression, we'll see that the position of P relative to Q is equal to RER, and R is constant and ER is fixed in the disk. The angular velocity of the disk as viewed by an observer fixed to the ground is the angular velocity of the shaft as viewed by an observer fixed to the ground, plus the angular velocity of the disk as viewed by an observer fixed to the shaft. The angular velocity of the disk as viewed by an observer fixed to the shaft is equal to theta dot EZ, and we already have the angular velocity of the shaft relative to the ground. So that tells me that the angular velocity of the disk as viewed by an observer fixed to the ground is equal to omega Ex plus theta dot Ez. So now we can use the fact that we need the final result here in terms of coordinates fixed to the disk. So if we look back on our diagram, we can actually see that Ex is equal to cosine theta Er minus the sine of theta E theta. And if we want to see that picture again, there's the direction Ex, there's the direction Er. Here's the direction E sub theta. And then this direction here is E sub y. And this angle is theta, which gives me that Ex is equal to cosine of theta times Er minus the sine of theta times E theta, which then gives me that the angular velocity of the disk as viewed by an observer fixed to the ground is equal to omega cosine theta Er minus omega sine theta E theta plus theta dot Ez. So therefore, we can now compute the cross product. The angular velocity of the disk as viewed by an observer fixed to the ground crossed with the position of P relative to Q is then equal to omega cosine theta times Er minus omega sine theta times E theta plus theta dot Ez crossed with RER, which is equal to, now let's do the calculations. ER crossed with ER is 0, E theta crossed with ER is EZ, and EZ crossed with ER is E theta. So I get R theta dot E theta plus R omega sine theta E Z. So therefore, the velocity of P relative to Q as viewed by an observer fixed to the ground is equal to R theta dot E theta plus R omega sine theta E Z, which tells me that the velocity of point P as viewed by an observer fixed to the ground, which is equal to the velocity of Q as viewed by an observer fixed to the ground, plus the velocity of P relative to Q as viewed by an observer fixed to the ground, is equal to, well, the velocity of Q is minus L omega EY, and then I've got plus R theta dot E theta, and then plus R omega sine theta E Z. And you can see that I've divided this up into two parts. One is the part that describes how point Q moves, and the other one is how P moves relative to Q. And we're going to keep these things split this way. So now what we're going to do is we're going to get the acceleration of point P. The acceleration of P in G is equal to d dt in G of the velocity of P in G, which is equal to d dt in G of the velocity of Q in G plus the velocity of P relative to Q in G, which in turn gives me that the acceleration of P in G is equal to d dt in G of the velocity of Q in G plus d dt in G of the velocity of P relative to Q in G. Now, if we define these respectively as the acceleration of Q in G plus the acceleration of P relative to Q in G, we can now compute each piece. The acceleration of Q in G, which is d dt in G of the velocity of Q in G because the velocity of q and g is expressed in coordinates fixed in the shaft, this is equal to d dt and s of the velocity of q and g plus the angular velocity of s and g crossed with the velocity of q and g. So d dt in s of the velocity of q and g is equal to, we have to go back to this velocity here, it's minus L omega Ey. And I didn't say omega was constant, so negative L omega dot Ey is that rate of change. The angular velocity of the shaft in g crossed with the velocity of q in g is equal to omega Ex crossed with minus L omega Ey, which is equal to, Ex cross Ey is Ez, so I got minus L omega squared Ez, which gives me that the acceleration of q in g is equal to minus L omega dot Ey minus L omega squared Ez. And then finally, the acceleration of p relative to q in g, which we've defined as the rate of change in g of the velocity of p relative to q in g, because that vector is expressed in coordinates fixed in the disk, that's the rate of change in d of the velocity of p relative to q in g, plus the angular velocity of d in g crossed with the velocity of p relative to q in g. And again, let's compute the rate of change in d of the velocity of p relative to q in g. What's that equal to? Well, let's go back and get the acceleration of p relative, velocity of p relative to q. Well, E theta and Ez are fixed in the disk, so this gives me r theta double dot times E sub theta, and then plus r times omega dot sine theta plus omega theta dot cosine theta times Ez. Right? That's what we got. And then the angular velocity of the disk as viewed by an observer fixed to the ground crossed with the velocity of p relative to q in g is equal to, well, let's go back to our expression for that angular velocity. That angular velocity is omega cosine theta ER minus omega sine theta E theta plus theta dot Ez crossed with the velocity of p in g, p relative to q in g, which is equal to r theta dot E theta plus r omega sine theta Ez, which is equal to, ER crossed with E theta is Ez, so I get r omega theta dot cosine theta Ez. ER crossed with Ez is minus r omega squared cosine theta sine theta E sub theta. E theta crossed with E theta is 0. E theta crossed with Ez is ER, so I get minus r omega squared sine squared theta ER, and then I get Ez crossed with E theta is minus r theta dot squared ER, which gives me that the acceleration of point P relative to Q in G, which is the sum of these, if I put these together, I get minus r theta dot squared plus r omega squared sine squared theta times ER. That's the ER component. And then the E theta component, I get plus r theta double dot E theta. And then I've got minus r omega squared cosine theta, sine theta, That's times E theta. And then the EZ component is going to be R omega dot sine theta. And then I've got plus R omega theta dot cosine theta plus 2R omega theta dot cosine theta, the whole thing times EZ. So if we rewrite that on the other page, because it may be a little hard to read on that last page, we've got minus R theta dot squared, and then we've got plus R omega squared times sine squared theta times ER plus got R theta double dot minus R omega squared cosine theta times the sine of theta times E sub theta plus, now I have R omega dot sine theta, and then plus 2R omega theta dot cosine theta times EZ. So then, the acceleration of point P in G, which is equal to the acceleration of point Q in G, plus the acceleration of P relative to Q in G, is equal to, let's grab the acceleration of Q in G, it's minus L omega dot EY, and then minus L omega squared EZ, and then we've got minus R theta dot squared plus R omega squared sine squared theta times ER plus R theta double dot minus R omega squared cosine theta times the sine of theta times E sub theta plus R omega dot sine theta plus 2R omega theta dot, I forgot the theta dot up there, cosine theta times E sub z. So you'll actually see here that again, we've got two parts to the vector. One part gives us the acceleration of Q, and the other part gives us the acceleration of P relative to Q. And the manner in which we decompose things is we take the derivatives separately for each part of the vector, and then we combine them when we're all done. And there's no need to have to combine them ahead of time, because that's going to create a lot more complexity in the algebra. It's a lot simpler to keep them separate, do all the calculations, and then add the results afterwards, where we can identify more clearly that how Q is moving and then how P is moving relative to point Q. Because again, in this problem we've got point Q moving in a circle horizontally, and we've got point P moving relative to Q in a circle vertically. They're moving about different axes, but what we're doing is we're decomposing the motion so that each part of the motion can be viewed independent of the other part of the motion, and then the combination gives you the cumulative motion, which is the motion of everything happening at once based on the fact that Q is moving and that P is moving relative to point Q. So that takes care of this example, and in the next lectures we're going to move on to other topics in kinematics that are important for other types of situations.